Anyways, do you like? What do you feel?
So, good evening, everybody, and welcome to the Department of Mechanical Engineering 3-minute thesis competition. So my name is Peter Brueggemann, and I'm the Director of Graduate Studies, so I have kind of the honor to guide you through this evening. And we have 12 participants, so we're really looking forward to, their presentations. What is this? Okay, I need to put it closer. Okay. What we're really doing here is, celebrating the work of our graduate students in mechanical engineering. And just to put things in context, like I mentioned, we have 12 presentations, but we have about 300 graduate students. Roughly 2/3 of them are PhD students, and also many of our master students are involved in research. Maybe a little bit less than usual, because if you look to the number this year, we had more than 65 graduate students joining our department this year, newly incoming students. And there are more than 42, we have 42 core faculty, but we also have a few affiliate graduate faculty that are actively advising these students and being part of the research program. What you will see is really a selection today of 5 areas where the department is taking significant action, also contributing to a better and more sustainable environment. Our department has huge efforts in making energy transition possible. Of course, we are also concerned and do a lot of research related to environment and making many manufacturing processes sustainable, but also kind of environmental remediation systems. You will see some examples of this. You know all that hospitals are more and more influenced the things they do from engineering, and I think mechanical engineering is also making huge contributions, particularly our department in this environment from a lot of biomedical companies is making huge contributions in that area. Manufacturing is traditional mechanical engineering, and we are pushing the limits. Everything needs to be better, faster, and more, sustainable in the future. And then, of course, there is also a large program on mobility and robotics in our department that helps many people and makes our society more efficient. So you will see the 12 presentations really cover these 5 areas and are a representation or a snapshot of the many great work that's going on in our department, but is maybe not presented here today. A little bit of history. So the 3-minute thesis, and putting it in context, it started in maybe 15 years ago in Australia as a kind of an experiment. Now more than 900 universities are doing these kind of competitions, more than 85 countries. And to put it in perspective, so if you want to maybe read through or attend a presentation of a PhD thesis, 300 pages is about 80,000 words. It would take you 9 hours, And so we are asking the students to actually bring the highlights of their work within 3 minutes, and they cannot use 1 second more to do that. So, cramping 5 years of research in 3 minutes, I think it's a real challenge, but it's something I think that our students are up to, and they will show this evening, that they can do this. The event is hosted by the ME Advisory Council that has many representations from local and international companies. And I think our colleague Ben Hoxie can maybe make a few words. He is the Senior Director of Danforth Power Solutions, and he is a member of the MEAC. Ben.
Thank you, Peter. Such a great list of topics here tonight. Very excited to see how you condense 80,000 words into 3 minutes. Word of encouragement. As we're all engineers, what really matters is our work getting out into society, and that's a lot about communication and how we connect it. So very much applaud the effort to practice this technique of getting your work out to the rest of society. The MEAC, Mechanical Engineering Advisory Council, is a collection of companies. You saw some of the names on the screen. There's a half a dozen of us in the room here today, and we really exist to bring the voice of industry, mostly locally here, as an advisory council, as the name says, for Sue and for the department. So things that we contribute beyond 3-minute thesis here, some resume reviews and practice interviewing for students as Career Day comes around, sponsoring and creating ideas and offering advisors for a particular undergrad senior council, or sorry, undergrad senior project. Student council, both undergrad and grad, we connect with and offer some advisory things, helping connect industry, what is transition from student to working look like, tours of different companies locally, things like that. So really help to bridge across. And shout out to faculty. One of our themes for this year is how do we help bring industry a little closer into academia. So if you're looking for guest speakers, if you're looking for ways to cooperate on research projects, let us know. Feedback to MEAC here, and we can help find places where that fits. So thanks to Peter and staff for putting us on. Excited to see you tonight.
Yeah, thank you very much, Ben. So maybe just a few housekeeping things and rules about and goal about a 3-minute thesis. So we have judges, and so there will be some prizes. But ultimately, we are selecting 2 participants for the CSC 3-minute thesis event. So the 2 best participants, selected by the judges will move on. And, the best of this competition will then move on to the university level competition. And we had great success in the past. And we hope we can continue, in the future on this. And of course, all of you, the winners will also get prizes sponsored by the department. And so let me introduce briefly the judges. So we have Katie Kruger for Thermo King and Train Technologies, who's sitting there. Yeah, if you want to stand up, that's great. But it's a small room now. So Biswa Mohanty, who is still at University of Minnesota, is Department of Neurology. And Ann Sheldon is retired Vice President of Product Security from Medtronic. And then we have Daniel Thomas. He is from Dunwoody College. He's there an associate professor. He is an alum, and he's not only an alum, but he is one of the former winners of this 3-minute thesis. So we thought it would be a good thing to bring him on. Yeah? He should know how it's done. No? So he should be able to judge. Yeah? So it's great, and thank you for your time. It's really great to have you here this evening. So what are the key rules? So every participant has made one slide, and so the slide will be shown during the presentation. There's no movement, so it's like a static slide that contains information that supports the oral presentation. Only 3 minutes, so 1 second more means the participant will be disqualified, and it can only be spoken word. So there are no props or no singing and other things. Even if you have a great voice, that's not going to be rewarded here. Clock starts. So we have in the audience, the clock will start when the presenter is saying the first words of the presentation. And then the decision of the judging panel is absolute. No, we have the full confidence in the panel, and whatever they say is law this evening. So what are the criteria for judging? So basically 2 parts. It's about comprehension and content. So, students should, of course, be familiar with the fact that the audience is typically a lay audience, no? So it is intended for non-expert. So there is a strong focus on background, significance of the work, what is kind of the contribution of the speaker to, what is being proposed of topic, the strategy, the approach that's being used, and then, of course, the outcomes and the potential impact of the work. We are also looking for, engagement and communication. That's, it needs to be clear, non-specialist audience, like already mentioned. The slide should support kind of what is said, no, and hopefully make things also more clear what is being described. And then, of course, students should be enthusiastic about what they do. Yeah, that's a key requirement, no? So you shouldn't be falling asleep during the 3 minutes. I would understand that for 9 hours when you present the entire thesis, but 3 minutes should be possible not to have this. Okay, so the program today is, we have now the presentations of the 12 graduate students. we also have not only the judges judging, you will have the opportunity to choose your favorite participant. So there will be a link after the presentations where you can select your favorite, and this participant, public's choice, will get a public choice prize, and it will also be awarded to that later on. In the break, then after that, the judges will convene in another room to select the winners, and in that time, Professor Mantel will make a few remarks about the department. After that, we have the award presentation, and there is some opportunity to network and to connect with all the participants, after that. So, okay, I think if I would be one of the participants, I took more than 3 minutes, I would be disqualified by now, and I think we should just move to the participants. So I think you all know, no? We come up, maybe you go up there, then you standing, there is a stripe here, no? This is where you will present. I will introduce each participant and move to the next slide, no? So that's ready for you, and then from the moment you start talking, your time goes. And then I think you know the routine about the mics, no? How we will switch that.
I'll check.
Yeah?
I'll do a
Okay,
check.
yeah.
You stand on the X.
Okay, so the first speaker is Jackson Wills. He is advised by Professor Perry Lee, and he will be talking about clean energy from ocean waves. So Jackson, whenever you're ready.
Do I need to do anything with the mic? Is it working?
Not gonna talk, let's see how it goes.
Hello, testing.
This doesn't count towards you.
Okay, good. Can you hear me? Is it?
That's good.
Okay, great. Do I have to do something to start it, or you start it? Okay. Hello, everyone. My name is Jackson Wills, and I'm here to talk to you about an emerging renewable energy resource, ocean waves. So if you've ever been in the ocean, you know how powerful it is. There's a lot of energy out there, and we can convert some of it into electricity without emitting greenhouse gases. So wave energy can provide 5 to 15% of our demand and provide energy much more consistently than other forms of renewable energy. As a part of our fight against climate change, we need more clean energy, and we need more forms of clean energy so that our grid is more robust to disturbances. Wave energy should be one of these resources. It isn't already for the reason that it's too expensive. These devices are too expensive compared with how much energy we receive from them. It's just not economical yet. So there's many designs for wave energy converters. The simplest is shown here. It's called a point absorber. There's a donut-shaped part that is constantly being moved up and down by the waves. That pushes on a piston that works like a bike pump and pushes fluid into one of these containers. Each container is at a different pressure. We can get electricity from these containers using the same idea as a water mill. So fluid pushes on a wheel and causes it to rotate, but instead of using that rotation to grind grain like a water mill would, we'll use it to spin an electromagnet and generate electricity. My work is on the controllers. So depending on which container we decide to pump to, the difficulty of pumping changes. So you feel this when you pump up a bike tire. It's more difficult to pump if the tire pressure is already high. So I develop algorithms to determine how difficult pumping should be at any time. If you make it too difficult to pump, the pump won't be able to move at all. If you make it too easy, you'll have to go up and down many times to get any meaningful amount of energy out. Getting the difficulty just right has a huge effect on how much energy we can get from the ocean. It's difficult to get the pumping just right because the ocean is very unpredictable. So it's difficult to know what's going to happen even a short amount of time in the future. The hope is that with this design, we'll be able to generate a lot of electricity using low-cost parts and make wave energy economical so that it will actually be used in place of greenhouse-emitting fuels. This will help us meet the climate goals that we need to meet as soon as possible. Thank you all for listening.
Okay, thank you. So we need to win some time for the judges, no, so that they can make notes. But in the meanwhile, I will introduce the next speaker, who is Haiwon Lee. She is advised by Professor Will Northrop, and she will be talking about ammonia as a hydrogen carrier. So if you want to come up and maybe test a microphone before it becomes official that nobody starts the timer. Just
Can I
test. Is it
test?
okay?
Good.
Okay.
Wait, don't start yet.
So just a second, and then.
I'm gonna give a timer to the judge. Gotta get it done. Okay.
So according to Energy Information Administration, in the past decade, around 80% of our energy was supplied by fossil fuels. On top of that, the world energy demand is expected to rise, and according to some sources, it's expected to rise by 40% in the next 20 years. So with that increase in energy demand, there is an increase in demand for carbon-free supply to reduce greenhouse gas emission and mitigate global warming. One of the solutions that we can think about is hydrogen, because hydrogen is carbon-free and it can be used to produce heat and electricity with only water vapor as a byproduct. But the thing is, hydrogen is very hard to store and transport. Hydrogen in its gaseous form has very low energy density per volume, which means that it requires larger vessels and containers to move it around and to store. And liquefying hydrogen is an option, but the temperature of the hydrogen has to be dropped down to almost negative 250 degrees Celsius, and it needs to be maintained at that temperature. So the whole process of storing and transporting liquid hydrogen is very energy intensive and expensive. To address these issues, ammonia can be used as a hydrogen carrier, because ammonia has very high hydrogen content. It has 3 hydrogen atoms for 1 ammonia molecule. And because of its prevalent use as a fertilizer, the infrastructures for its storage and transportation already exist. Now, when ammonia is transported and distributed to the different sites that require hydrogen, it has to undergo a chemical reaction called ammonia decomposition. And during this reaction, ammonia is decomposed or broken down into nitrogen and hydrogen. And this reaction also often occurs in the presence of a catalyst that facilitates the reaction by lowering the energy barrier. The most active catalyst has ruthenium, but ruthenium is a very precious metal, which means that it's expensive and very scarce. So finding an alternative that is more affordable and abundant is important. Of many candidates out there, nickel has proven to be reasonably active and very cheap. For comparison, 1 pound of ruthenium is almost $7,000, while 1 pound of nickel is a little under $9. So my research focuses on using nickel-based catalysts to produce hydrogen from ammonia. With the use of a nickel-based catalyst and better understanding of how it works, maybe we can potentially contribute to bringing the world one step closer to carbon-free future. Thank you.
Very much. So the next presenter is Tanukav Srivastava. He's advised by Peter Bruggeman. And well, I was just checking if you still remember my name. And he will be talking about mitigating forever chemicals in groundwater using plasmas. And again, we should probably wait a little bit on the judges. So they all failed in their 3-minute competition already. No, they take too long time. But so Tanukav, if you standing on the spot, and we move the slide forward. So and they will give you a sign. But
Yeah, I can just test. Yeah,
Good.
is that good? Yep. Do you know how many harmful chemicals are present in the water that we all have been drinking today, according to the Environmental Protection Agency? The answer is about 15,000. These chemicals are known as perfluoroalkyl substances or PFAS and are often produced by industries for regular household products like cookwares, paints, shampoos, detergents, etc. The problem with this is that PFAS during industrial wastewater discharge often enters our groundwater, which is the major source of drinking water for over 50% of the population of the United States. Aside from being harmful for the human body, these chemicals are what are known as forever chemicals because conventional water treatment techniques are highly inefficient in removing these chemicals from the wastewater. Also, therefore, it's no surprise that these chemicals can easily enter water that we all have been currently drinking. Studies suggest that 45% of the tap water in this country consists of PFAS, and that is a testament to how hard it is to decompose these compounds. So, what do we do in this situation? Well, luckily for us, plasma offers a solution. Now, all we need to know about plasmas in this context is that they are a chemical cocktail of reactive molecules that enable PFAS decomposition in water when they enter the liquid phase. So, and studies have also shown that plasmas are more effective in removing PFAS from liquids compared to other conventional water treatment techniques used in industry. However, the implementation of plasma-based groundwater treatment is not so simple. Plasma-based groundwater treatment reactors often have complex transport limitations associated with them, which reduce their energy efficiency. So my research here is focused towards developing a highly controlled plasma liquid reactor for which we can demonstrate for its efficiency using some small, simple molecules like formate and then extending it to tackling PFAS decomposition. The idea behind this is to obtain a framework and obtain some parameters for high efficiency industrial scale plasma based groundwater treatment. This is important for us to obtain safe drinking water in the future at low energy cost, since water arguably is one of the most important natural resources for sustainability of human life. Thank you.
Thank you, Tanubhav.
Oh.
This way, yeah. So the next presentation is from Clifford Gortemiller. And so he is also advised by Professor Will Northrop. And you might kind of remember the word ammonia from before. It's apparently an important topic, at least 2 presentations today. So he will be talking about burning ammonia, no-fuss approach. Again, waiting a little bit, but I will move forward. Maybe, Cliff, you can put yourself on the cross here so you can test your mic if it's okay. So we are good to go. The judges are
Awesome. What if I told you that there was a molecule that is carbon-free, energy-dense, produced in huge quantities, and easily handled with existing infrastructure? Today, I'm going to tell you how to burn ammonia using nothing but the air around us and a device so simple that each and every one of you could build it when this presentation is over. Ammonia has attracted interest in recent years because it is an amazing molecule. It is energy dense, and 2% of the world's total energy production goes into making ammonia. It's most commonly used as fertilizers, and it's not an exaggeration to say that in many situations, the dirt just keeps the plants upright while we spray ammonia on them to make them grow. But ammonia is also attracted interest for its use as a fuel. Again, because it's full of energy. But ammonia has 2 problems as a fuel. First of all, it's considered non-flammable, does not like to burn. And second of all, when it does burn, if it burns under the wrong conditions, it tends to emit a great deal of hazardous air pollution. We have solved these problems using a swirl burner. Our swirl burner, you can see here, consists of 3 parts. On the bottom, it's got a premixer where the ammonia and air are mixed together. The mixture is passed through the swirler and then into the flame holder. It's the entire life of the mixture in the swirl burner. The swirler tends to twist the mixture, and because it twists the mixture, something amazing happens. When the ammonia-air mixture enters the flame holder, it actually sits there in a little island, perfectly stationary, right where that green dot is. And this creates a recirculation zone downstream, which is an ideal environment for a non-flammable fuel like ammonia to burn. This also has interesting implications for burner design. Because the recirculation zone must fit in the flame holder, that means the flame must also fit in the flame holder. Therefore, you select a flame holder diameter based on the minimum size of the flame that you need, and you select a flame holder height based on the maximum heat output you need out of your burner. This is also beneficial because the burner can adjust its heat output without any moving parts when using only one nozzle. So designs are very simple. So how do you build a burner like this? First, you select those parameters, then you cut some metal and enjoy the warmth of a carbon-free fuel. That's it. Thank you for your time.
Yeah, thank you very much, Cliff. So the next presenter is Ian Song, and he is advised by Professor Natasha Wright. So he will be talking about renewable energy from beer and chips, which we all love, of course. And so we'll move to your slide and, take place on the cross, if you want. Can you test? Okay.
Yep.
So you're ready? Judges are almost ready. Okay.
All right. I'm going to start with a quick poll. How many people here enjoy coming home after a long week and popping an ice cold beer? Amazing. So what if I tell you that the production process in making those Friday night beers could also be a source of renewable hydrogen energy, and it could support the United Nations Sustainable Development Goals? The production process for beer, potato chips, candy, and other staple snacks produce a stream of highly concentrated wastewater known as high-strength wastewater. Surprise. And we can use this or the organic matter in these high-strength wastewater to create renewable energy in the form of methane and hydrogen, collectively known as biogas. However, currently, most manufacturing plants will simply pay the city to treat and dispose of the wastewater, which is quite literally a waste. Because what the city does is that they take the high-strength wastewater, they dilute it with lower-strength household wastewater and treat them together. Although this process will still allow us to harvest some of the renewable energy, it does so significantly less effectively due to the dilution that they have done previously to the high-strength wastewater. So our project team is proposing a small-scale modular wastewater treatment process to be installed at the food and beverage manufacturing facilities. This tackles a few key challenges in the current scheme of wastewater treatment. The first is that it saves the manufacturing industries money from not having to pay the city to treat their wastewater anymore. Second, you can get a higher efficiency in producing your renewable energy in the form of your biogas. And third, the produced biogases could also be an additional stream of income for the manufacturing facilities. My specific part of the project focuses on how to recover these biogases most efficiently through the wastewater treatment process. We do this using a membrane gas recovery system. We've specifically, so I have developed a model in order to for this gas recovery system that we're going to use in conjunction with a bioprocess model from our collaborators over in the at UIUC, so that we can optimize these small scale systems and make it as cost effective as possible for our favorite manufacturers. Now, we are performing a pilot of this small scale system here locally at Fulton Brewery. So the next time you go and purchase Hop Kingdom or something from Fulton, know that you're also supporting our efforts to produce renewable energy from these high strength wastewaters. Thank you.
Thank you very much, Ian. And so the next speaker, and we are roughly halfway, is Sujit Karthik. So he is advised by Professor Mike McAlpine, and he will be talking about 3D printing, tiny pipes, and valves. If you can take your place, and microphone works, great. Just give a second to the judges and we can get going.
Will you give me a heads up when I can start?
Yeah.
Yeah. Healthcare is expensive, and it is a concern for all of us here. One effective way of addressing this problem is by reducing the cost of everyday medical examinations like blood tests. Now, imagine the impact that can be created if we only require a single drop of blood for these tests. It can reduce the amount of materials required for these tests and subsequently reduce the cost of the test. This is an important step to make healthcare affordable for everyone. But why is this dream not a reality yet? Well, there are many challenges that researchers face that is stopping from this becoming a reality. But today I'm going to talk about a couple of challenges that I'm trying to work on. Firstly, to efficiently use a single drop of blood, we need very tiny pipes. Pipes that are so small, they make your human hair look like giants. The traditional way of manufacturing these tiny pipes is complex, expensive, requires experts, and also requires huge facilities. But what if we could 3D print them? Something that anybody can do in any room in the world. That is exactly what I do in my research. I use a material which comes as a thick paste, and it has a unique property. This property is that when it reacts with the moisture in the air, it turns into a rubber band like solid material, which makes it perfect for 3D printing. And guess what? This is the same material that we use in our bathrooms and kitchens to prevent water from seeping into the walls. So it's a no-brainer to use this material to 3D print tiny pipes where liquids cannot leak out of. But hold on, just having tiny pipes is not enough. We need a way to start and stop the flow that goes into these pipes. This is the second challenge, and for this we require valves. So these tiny pipes are just like straws. When we squeeze a straw, the flow inside it stops. In my research, I tried to figure out a mechanism to recreate this squeezing action by 3D printing a very tiny but strong box around these pipes. When this tiny box is filled with air, it creates such a strong force that it squeezes the pipes inside the box, causing the flow to stop. And when I remove the air pressure, the flow continues again. So the final aim of my research is to create a 3D printed device that contains a network of these tiny pipes and valves. Like me, many researchers around the world are tackling the different challenges to make a single drop blood test a reality. And all these innovations are just like small drops, but when they come together, they're going to create a massive wave that is going to change healthcare forever. Thank you.
Thank you, Karthik. And this is really impressive. No, most of our participants don't even need 3 minutes to make the statement. So the next presenter is Ting-Wei Chen. He is advised by Professor Terry Simon. And so he will present his research on reducing CO2 emissions in aircraft propulsion systems. So Ting-Wei, if you want to take your place here, and then we briefly wait on the judges.
I start? Okay. Okay, so I will start. Okay, so I'm Tingwei Chen. Today I'm going to introduce my research. I believe climate change is one of the most significant problems in our generations. Currently, we produce more than 1,000 tons of carbon dioxide into the atmosphere. If we keep producing the carbon dioxide like the current rates, the Earth temperatures will rise about 3 degrees in the next 30 years, leading in a huge amount of loss of species and creates a huge amount of the climate refugees. So it is extremely important for us to reduce the carbon dioxide emissions. Currently, in the aspects of the transportations, although the global efforts is working on develop the advanced technologies like the electric aircraft and rocket transportations, we still highly rely on the traditional aircraft engines to satisfy our transportation need. So my research aims to solve this. My research aims to increase the efficiency of the conventional aircraft by reducing the amounts of the fossil fuel we consume and reduce the amounts of the carbon dioxide. So if you look into the gas turbine engines, the entire process between with the compressors, which the air is in it, then the air will get into the combustor with the combustions, then passing through the gas turbines. And the most important thing is that the efficiency of the engines is relies on the temperature of the existing gas from the combustors. If we could raise the temperature of the existing gas from the combustor, we could generate higher thrust to propel the aircraft. And however, this efficiency is limited by the temperature that the gas turbine could sustain before it melts. If we could better protect the gas turbine from the hot temperature mainstreams, we could better raise the efficiency of the aircraft engines. So how do I solve this? My research introduced the cold air from the compressors to generate the barriers between the hot mainstreams and the gas turbines. With these barriers, the gas turbine could sustain a higher temperatures from the mainstreams and could better be prepared and sustain a higher temperatures. As a result, the gas turbine could sustain a higher temperatures, the efficiency of the engine could be raised, and we could consume less fossil fuel and reduce the carbon dioxide which is emitted in the atmospheres before we reach the net zero at 2050.
Thank you very much, Tingwei. So the next presenter will be Beatrice. I think I was allowed to say that Beatrice made a mistake, actually. She graduated a few days before the 3M thesis, so she is not officially part of the judges competition, but the audience is allowed to vote for her, as a favorite. Yeah. And so this is the only time you can make a mistake by graduating early, I mentioned already.
I know.
And so she is advised by Professor Al Axon, and her research is about self-limiting bacterial growth in hydrogels. And so move forward.
All right, should I just wait?
That's good. I think you can go ahead.
Yeah. Okay. What's the first thing that comes to mind when we say bacteria? I bet that some of your first thoughts were either germs, infections, or diseases, am I right? What if I tell you that bacteria are one of the oldest life forms to appear on Earth, and that human beings have been using microbes like bacteria for over thousands of years to make bread, beer, wine, and also in many agricultural practices? Recently, by combining the dynamic features of these organisms with synthetic materials, we can create these incredible hybrid materials, where the function of these organisms can be enhanced by the protective and stable environment provided by the material. So these hybrid materials can also be called engineered living materials, and they have many applications in our day-to-day life. So therefore, optimizing these engineered living materials can be beneficial to remove pollutants out of water, to help create healing patches that can release antibiotics locally to help heal wounds faster, and also to detect blood or toxins, for example. So therefore, understanding how bacteria grows in tight spaces is essential to improve the function of these living materials. So imagine that the materials are like living homes for these tiny creatures, the bacteria. So when you place these bacteria in tight spaces, they grow and form chain-like structures that continue to duplicate exponentially as long as nutrients are provided. However, they are still in a tight space. So as they are growing, they deform, they exert a lot of stresses to their surrounding material, which as they're constantly pushing, it continues to grow. So, however, they are still in a tight space. Sorry. So therefore, what we saw observing my research was that as the bacteria was growing, they started to deform the surrounding structure of the material. So which led to the development of an impermeable barrier where the nutrients were not able to reach the bacteria anymore. So when the absence of the nutrients caused these bacteria to become more compact and a stable form, where they protected the genetic material by forming spores. And it's like hibernation, essentially. So they became extremely resistant to environmental stresses. So by understanding how this behave, what we observed was that bacteria grow in tight spaces, behave in a self-limiting way. And by understanding how they behave in tight spaces, we can essentially develop better and more efficient materials that can help clean up the environment and also deliver medicine in a clever way.
Thank you, Beatrice. So the next presenter is Supam Dongarwar. Well, I'm the advisor. You already know my name. And so he will be talking about can plasma help us create a healthier environment? So Supam, if you want to take your place, I don't think we need to wait on the judges now. And whenever you're ready, for once, no, sorry. And whenever you're ready, you can start, Supam.
Here by vehicle powered by gasoline or diesel. I bet almost everyone, right? Do you know how much the exhaust of this vehicle contributes for the air pollution? It's more than 50%. The major culprit is the NOx gases, which is a group of nitrogen oxide. It's highly poisonous and it's around 300 times worse than the carbon dioxide for depletion of ozone layer. This can form the acid rain and causes several respiratory diseases. Well, you might think that we can get away by using the electrical cars and vehicles, but the reality is that heavy loading vehicles relying on gasoline and diesel are not going to away soon in the near future. Currently, catalytic converters, which are also recently in the news because of getting stolen away, are used to reduce this NOx using chemical reactions. However, more than 80% of the pollution is still released during the engine warm-up period. That is also known as the cold start problem. This is because the catalytic converter needs to be warmer for them to reduce the NOx effectively. This is the significant challenge, and what can be the solution for it? It turns out plasma in conjunction with the catalytic converters is a promising solution. Plasma can convert electrical energy into highly reactive species, which can reduce the NOx without the need of initial warm-up period. And this way, we can overcome the problem of initial cold start problem. But the question is, if plasma can do the job, then why do we still need the catalytic converter? Research has shown that the combined effect of plasma and catalytic converters is significantly higher than their individual effect. Then you might also wonder, if this is that good, then why do we still not implementing this? The key challenge is finding the optimal operating conditions, and this is where my research lies in. My research is about implementing diagnostic, to find the key chemical reactions for removal of NOx at ambient temperatures with the goal to allow us to find the optimal operating condition. This has the potential to reduce the air pollution significantly, and that will be my contribution to the healthier environment. Thank you for your attention.
Thank you, Supam. So the next presenter is Lakshi Gangwar, and he is advised by Professor John Bischoff, and he will be talking about what the research is, can we preserve organs to save lives? Technical. Can you, is this okay?
Test.
Yeah. Okay, good.
Well, many of you may have heard the rumors about Walt Disney being frozen, or some of you may have seen Austin Powers' cryo sleep chambers. Even though those are fictions, they have roots in physical and biological principles of cryopreservation. Cryo meaning cold, preservation meaning maintaining something in an existing state. So to motivate the work of my thesis, let me ask you, do you have a friend or family in dialysis waiting for a kidney? Or do you know how many people are on an organ transplant wait list? More than 100,000 people are on an organ transplant wait list. And by the end of 3MT talks, we'll have a new patient added to that waiting list. So on one hand, 20 people are dying for an organ. On the other hand, 80% lungs, 70% hearts, 30% kidneys, which are donated, are still discarded because these organs have a very short shelf life, few hours for a human heart. So how do we, if we can extend the shelf life of these organs, we can possibly eliminate any wastage. And we are talking about 5,000 kidneys to 9,000 organs per year to save. So organ cryopreservation, how does it work? For organ cryopreservation, we take an organ, we cool it down to cryogenic temperature where it transforms into a glassy state, and now you can store that for months. So how do we rewarm these organs? Think like you have your frozen food and you put it in a water bath, and you are thinking your food is still soft and mushy at the edges, but the center is still cold. That means water bath rewarming is convective. So our lab device, something called nanowarming, where we put nanoparticles inside the organ's blood vessels, and now they generate heat in magnetic field, lighting up like a tree lighting from your branches. So with using that, our lab and others showed the success of cryopreservation at a rat organ scale, as shown in there. So my thesis work was to take that from a rat organ to a human organ and try to scale that and show physical success by cooling and rewarming liter volumes of CPAs, which are relevant for human preservation. Now, to conclude that, I will tell you a real life story, the impact this research can make. There is a Minnesotan boy named Carson who was 2 months old and he was needing a liver transplant. 18 years later, he graduated with a viral proud head. And my research takes a step forward towards promise of human organ cryopreservation, giving people like Carson, allowing them to play, graduate, by enabling them the gift of life. Thank you.
Thank you. Thank you. We are at the last two presenters, and so Hamid Aloy? Yeah, sorry. Difficult name, sorry for me, at least for me, sorry. And so he is advised by Professor Raj Rajamani. And yeah, I'm not sure if I can do this honk honk, but okay. I'm sure you will do it better than me. Please don't hit me. So intriguing title, yeah. So we move to the slide. Maybe wait a second for the judges.
Sure. Do you have, is it okay, the microphone? Okay. Hi, I'm Hamid Reza Alai, and I'm here to share with you the idea of having smart e-scooters that can protect their riders. E-scooters are great last-minute micro-mobility devices, and actually they're very fun to ride. But also they're very vulnerable to crashes. Imagine that you're sitting in a car and you have a small fender bender accident. Nothing really happens to you. But if you're riding an e-scooter and you get hit by a car, you might get severely injured. In fact, from 2017 through 2021, an average number of 64 e-scooter riders per day went to emergency departments. So that's huge. So what's the solution? One solution is to equip all the cars and vehicles on the roads with the existing expensive technologies to detect these scooters and avoid a collision with them. But it might take many years or decades for such expensive technologies to get incorporated to all the vehicles, and we don't have that time. So our approach is to develop low-cost technologies instead that could be used right away on today's e-scooters. We use very low-cost sensors attached to the e-scooter to not only detect the vehicles surrounding them, but also to track their trajectories and predict any car or scooter accident. If the danger of an accident is predicted, the system will warn the vehicle drivers about the presence of the e-scooter using a loud warning audio like a loud horn so that they can react accordingly and avoid the accident. We have multiple challenges in this project. The first challenge that we're facing with is that the sensors we use only provide us with the location of the surrounding vehicles. But what we need to know to predict the accidents precisely is to also know their speed, orientation, other factors. So to overcome this problem, we develop estimation algorithms to use the limited information that we have to estimate and predict other variables such as speed and orientation. The second challenge that we are facing with is that we are using very low-cost sensors, and the performance of these sensors are not even close to the sensors being used in autonomous vehicles. For example, their accuracy, their robustness is not even close. So to overcome this second challenge, we do sensor data fusion. For example, we have a 2D LiDAR attached to the e-scooter in front to monitor the traffic, and that sensor is very sensitive to the slope variations of the road. We use a single camera and combine the data from these two sensors to improve their performances and have better tracking, vehicle tracking. This is a very exciting project, and we hope that the results in the future help us to protect e-scooter riders from car accidents and also lower down the price of existing collision warning systems that are being used in autonomous vehicles. Thank you very much for listening to me.
Yeah, thank you very much. And we are the last presenter for this evening. This is Caroline Berneman, and so she is advised by Professor Natasha Wright. And we'll be talking about affordable home dialysis in low-income countries. So if you can take your place, we move the slide and give the judges a minute.
Okay.
Okay, test the mic. Okay.
Yeah, should be good. There are 200,000 Nigerians with kidney failure who do not receive adequate dialysis, the life-saving treatment they need to survive. This number represents around 99% of the total Nigerians with kidney failure. 99%, meaning that nearly all of the patients with kidney failure in Nigeria will die far sooner than they should. Not because a treatment doesn't exist, but simply because they can't access it. My team has conducted over 150 interviews with dialysis stakeholders who have emphasized that the barriers to access extend far beyond just limited dialysis centers or machines. Patients on conventional dialysis must go to the hospital multiple times a week for treatment. Dialysis can be very expensive, but the indirect costs are often even bigger obstacles. This includes the time for treatment and transportation, plus lost income for patients and their caretakers. So, what can be done to improve dialysis access? One solution is expanding the use of peritoneal dialysis. This treatment is becoming more popular in the US and many other countries, but is still uncommon in Nigeria. Unlike conventional in-hospital dialysis, peritoneal dialysis can be carried out by patients in their homes. It doesn't require an expensive machine, consistent power, or significant healthcare labor. This means it can have much lower direct and especially indirect costs. However, it does require large volumes of peritoneal dialysis fluid, which is not widely manufactured in Nigeria. Because of this, peritoneal dialysis is currently too expensive and inconsistent where it could otherwise be a life-saving option. And this is where my research comes in. Peritoneal dialysis fluid, much like IV fluids, is mostly made up of water, which is heavy and expensive to import. Rather than doing this, my research focuses on designing a system to produce this fluid near the point of care, in hospitals around Nigeria and in other low-resource areas. The system will purify water, mix in solutes, and package the fluid to be used for in-home treatment. Now, you might be thinking that this concept seems pretty straightforward, but the key challenge is doing this within the context of a hospital with limited resources. For in-home treatment to be an option, the fluid must be safe to use for at least a couple weeks. This means that the number of harmful microbes in the fluid must be kept extremely low. Clean rooms and autoclaves, which would typically be used to achieve this, are infeasible due to their high costs and power consumption. Instead, I'm evaluating lower cost options to be incorporated into the system design, such as filtration, ultraviolet light, and chemical disinfection. I'm also exploring novel strategies to control microbial growth post-production. We're currently evaluating these methods with biological testing to help us engineer a system that's both effective and economically viable. Right now, 200,000 kidney patients in Nigeria and over 8 million around the world are almost guaranteed to die prematurely. But this doesn't have to be the case. My research aims to enable affordable in-home dialysis where it's needed most. Thank you.
Thank you very much, Carolyn. So I would like to really thank all the students. I mean, to actually come up here, be courageous, to present all your great work, in less than 3 minutes. And everybody succeeded actually in less than 3 minutes. Is really impressive. And I know that many of you spend a lot of time preparing this, to really give the best of yourself. So let's give them all a round of applause. So I think the judges probably want to withdraw for making their deliberations, for selecting the 2 winners. I think there is a room prepared for you. Yeah. There is a slide. Okay. But, okay. And then, so while the judges are deliberating, there are 2 items. So one is, the audience is also able to vote. And so if you go to the link, z.umn.edu choice ME3MT, or you scan with your phone this barcode, you should have the opportunity to vote. So students can vote on themselves. No, I don't think that's the limitation. So that's okay, but that's probably not helping. No, you all get 1 vote of yourself. And so this will be open, and I think the names of both the titles and the names of the participants are there. So also for those remotely, you can use this link to do this. And during the break, while we are waiting on the judges, Professor Mantel will present some information out of the department.
But I'll leave these slides up for a couple minutes while you vote, okay? So I'll leave a little bit of space here. Then I have some interesting then and now history things for you for mechanical engineering. So this is kind of, we stall until the judges are done. I have some jokes. No. Yeah, my thesis was a long time ago. The predecessor to additive manufacturing. So before then, there was a way to make parts out of composite materials when you take a toe and you could place it in a shape. So very much like what happens in additive manufacturing, but we only had, we used lasers to heat it up or other kinds of sources, but same kind of problem: heating, placing the material, making a shape, but only very basic shapes. How are we doing with voting? Thumbs up? Everybody's okay. Okay, so I'm going to switch. I have so many All right. So I first of all, I wanted to put these on a rotation before while you were all sitting down, but I forgot. So sorry, because more our communications person took a lot of time to put this together, and I think this is really fun. We started this 3-minute thesis in 2019, and so this is our 5th annual, and we've seen quite a few changes. But and originally we were in the Black Box Theater over in Northrop, but you can see some of our early winners. I don't know if any of you recognize any of these students. One was in Professor Hong's group, and then another, let's see, with Professor Abel, yeah. And then second year, 2020, notice the pictures. Why do you think this was? What happened in 2020? Yeah, yeah. So we had COVID, because it's always been in the fall and October. So we were virtual. Let's see, is Daniel in there? No, yep, here he is, right? One of our judges, bottom left. And that was his poster. So ammonia's been around for a while, and then the third year, 2021, we're still in the middle of the pandemic with our masks. There we are. I haven't aged. Mask hides everything, and it's our winner. And again, this was our other venue. We decided to move it closer to the building, and again. Now, this is last year, 4th year, 2022, all of the presenters. So we have and now we're back in this space. Our winner from last year, working with Professor Abel, Barrick. Jim Vandevin, he was the Master of Ceremonies last year, our DGS. And today, this is our 5th year. So first, let's just, because we might forget, but we won't, but let's thank all of our 3-minute thesis presenters for this year. They're quite brave. So now what I have is actually a very interesting set of slides. I just have to make sure I have too many things open here. I apologize. Nobody's helping me out. Let me go to the downloads. Maura, what's it called? None of those. Okay, I know where it is. That's why, because it's on Google Slides. So I asked Maura if she'd put together some things then and now. I think you're going to find this really quite fun. So I don't know if you haven't been in our building, if you're an alum, please walk back through ME. One of us can let you in to check out the new murals. And the space is quite updated. Here's a few things. I think these are a little bit different than what Peter presented, but size, number of faculty members. I think we're really proud of our graduation placement rate at 98.3 is pretty impressive. Our students go to some major companies and also into academia. So here's a few quizzes. So I'm going to leave this up. It's kind of like the slideshow at the movie theater. What do you think? Retractable seatbelt. Somebody knows, right? And here is a little bit of the facts, so I'll leave that for you to read. And actually, the department head holds the title of the James J. Ryan professorship in honor of this particular faculty member. So it goes with the department head. And there's a nice picture after this, so you've all had a chance to check that out. I'll leave that up for a little bit. See if you can navigate where you are. Do you see some of the buildings that should be familiar to you on campus? We have some alums. Did any of you know Professor Ryan? No? Okay. So, but I think these are true, true pictures. This is one of our most fun pictures that we've come up with recently. So we've always had this class picture from the class of 1943. And that was in the main office. And then recently, for our graduates, class of 2023, we asked, this is our most of the class, they were all in senior design, and it was last spring. We had them come out, check it out. It's the same, close to the same backdrop. It's the same building, but it's been renovated. Quite different look in our class. And again, our students are always building things, as you know. So we're about to get this donation of a student-built, that is a motor for a boat. And that was built here. We used to have a foundry in the basement. I think some of us, when I first started 30 years ago, the foundry was still here. And maybe for the first 10 or 15 years of my time in the department, we still had foundry as part of one of our classes. So, but now, you know, students are building things with electronics, and you see some of the differences in people's PhD topics too. But
that was a requirement to build that. Funny, it's like that.
He had one too?
Well, but he ended up, the depression started, and he ended up not finishing. But I know I'm talking about doing that, building a monster.
Building the motor?
For a boat motor, yeah.
Yeah, yeah, and then maybe they made you go out to the boundary waters and see if it really worked, right? Oh, no, wait, no motors in the boundary waters, right?
Right.
Yeah. Then you could?
Yes.
Oh. Yeah, right then. Engines lab. So this really, Maura, is that true? That's an engines lab picture? You didn't get that? It's amazing. So that, the engines lab. And now this is our new engines lab. And of course, we used to have engines lab. Most of the bulk of all the engines lab was on the 4th floor of mechanical engineering, but now we've moved it off campus. We have a small engines lab on the 4th floor, but we can only have a certain amount of fuel there. So that's why we have it all located off campus. How many of you that we're speaking today work in the engines lab? Yeah. So none of you are in this picture though. I think that engine might be still in this building. Is it? Is it not at the engines lab? I don't think so. Here's another classroom. Classrooms have changed. I don't think any of our alums that are here right now were in a classroom that looked like this, but classrooms have changed and we have more of these active learning style rooms. So that's about 100 years. Okay. I leave this. I know a number of people in this photo, but I'm not. I'm definitely dating myself. Any of our alums in here know any of them? How about Dick Goldstein? Pick out Dick Goldstein in this picture. Yep, he's second from your left. Eve Sparrow. Anybody pick out Eve Sparrow? Mike, where is he?
Lower left.
Yeah, right next to Dick Goldstein.
Yeah.
Another person I recognize, Ernst Eckert. He was about 90 when I joined, so he's very famous. Eckert number. And he's got the well, they all have the glasses. That's right. Yeah. He's the glasses. No, he's 4th from the left. Very much smiling. He's kind of in charge. At that point, I think he might have been. I don't know if he was ever department head, but he was in charge. And there's another person. I don't know if any of you knew Warren Eibel. Warren Eibel. I'm pretty sure he's on the far right.
It's just 2 blocks away from me.
Yeah. And there are probably other faculty in this picture, but these are all faculty that I knew when I came. When I came in 1991. So, and I'm not sure what year this picture was taken. I'm not sure that we know either. But gentleman is Dr. Sparrow. Left corner, front row, arms crossed like this, right next to Professor Goldstein. They were about the same time. They arrived probably within a year or two of each other. There was always this competition who was here the longest, because I think Dr. Goldstein was here as a postdoc or something like this and then came back. So he had a longer time at the U. And then I guess, for the women who are in our group, the first graduate was in 1934. And it's kind of a sad story because, although she was really quite a good student, she ended up doing kind of a secretarial job. So, and there's a kind of a spread that we did in one of our newsletters. But what's not on here actually is I think it is our first PhD student, is president of university, Jahathi, what's her Murthy, and she's president of Oregon State University. So the first woman, PhD, and her advisor was Suhas Patankar. She did some numerical things, and I think her graduation was in the 80s or something like this, definitely before I came. She's not listed here. These are more of the students that were as undergrads. And I guess something new, I'm doing really well on this, huh? So we only have a couple more slides. Good job, Maura, in taking care of my communications here. So student group, She Is Me, is a new group that started under Professor Korchag and the head before me. And we have 2 student groups that are She Is Me, one for undergrads and one for grads. This is kind of fun. I don't know if, Peter, did you know about this plasma cutting jack-o'-lantern activity?
Plasma is used for everything.
I can see this. Yeah, plasmas are for everything. Yeah, yeah. Peter, once you're ready, you can reconnect, and then I can just change over the control to yours. And then just to kind of bring it back to 2023, first day of classes, donuts. And any of you have donuts the first day of class? Did you walk through the main area? All right, good. So, and I think this is actually a social. Yeah, ice cream social. So with that, I thank you all for hanging out while we wait to hear from our judges. And we're going to first call all of you presenters up individually, because we have a certificate and we also have some swag stuff we all get. Okay. So with that, I'm going to pass this to you. I was on. And let's see.
USB-C.
USB-C, and then.
Yeah, it's good. It's good.
Okay.
Oh, no, this is not okay. Okay. Good. No.
We don't want to make sure I get them both on.
No, it's okay. Oh, you want the other one? Okay.
Yeah, or I can just shut it down. Yeah. Are you're really USB-C? Main presentation?
Yeah, it's okay. It's on here in the center. I think it's okay. It's not.
Okay, let me. Will that?
Okay. So thank you. So first, I would like to call all the participants here, and Ben, could you maybe?
This way?
Okay, Ben. Okay, Ben left. Oh, okay, had to leave. Okay, so Professor Mantel will give you your certificate.
For an alphabetical order.
And it's in alphabetical order this time. Okay, so Hamid Aloy. So congratulations. Carolyn Berneman.
Yeah.
Okay, yeah. Ting-Wei Chen. Beatrice de Sosa. Supham Dongarwar. Lakshi Gangwar. Cliff Gortemiller. Sujit Kartik. Haewon Lee. Ian Song. Tanuphav Srivastava. Jackson Wills. And I mean, I hope for all of you, I mean, there can only be one winner. Maybe we have 2 or 3 winners today, but I think it's a great experience. I think that you should see this as an opportunity, the practice, learning to deal with stress, in front of a critical audience that is judging you, and surviving this and doing a great job. I mean, you should all be proud, and thank you so much for all your efforts in doing this. So before we announce the prizes, because I'm sure we lose everybody's attention after that, I would just like to thank everybody who organized the event. And I was of no help because I was traveling the last week. And so basically it was Professor Mantel and our excellent staff, that's also here present, Maura, Gillian, Carrie, Jennifer is not here, who did a lot of work, and John. And another Jennifer Clark, who really did all the heavy lifting and made this event possible. So let's thank them also for their efforts.
Give a swag to the judges now. I think it's
Okay. Yeah. So we also have a little attention for the judges. So thank you so much for, but a little attention from the department to thank you for being present here and supporting our graduate program and our students in all their efforts. So thank you so much. And of course, everybody being here, is really, really great for your support, and we are grateful for the continued support of our program. So now, we are waiting on the prizes, no? So we have, I think we start with the second place, which is awarded by the judges, no? To, okay, why is this not, okay, Haiwon Lee. So please come forward, and so yeah, and so it's my understanding we also get some small monetary prize that will be given later. Yeah. So it's not for free that you have been talking today. Yeah. And so the first prize for selected by the judges from this competition is going to Caroline Dornemann. So both of you you will get an email from me. You need to register for the college 3MT event. No, you need to do this actually today, because I think today is the deadline. And it's next week, or I forgot the date, but soon, 2 weeks from now, you will be competing with the rest of the college, and I'm pretty confident that you will do excellent, and we will be proud of you as a department. So thank you so much. And now the question is, does the audience agree with our esteemed panel? Sometimes it does, sometimes it doesn't. But this year, actually, there is a very good agreement, and the winner for the People's Choice Award is Caroline again. Congratulations.
You haven't been in any pictures.
That's okay. I should go
You're
down.
down. Yeah, we should stand. And 1, 2.
Okay, so sorry. So, well, thank you so much, everybody, for being here. Also, thank you for those who joined virtually. Again, thank you for your support. And for those present here, we have an opportunity to network and some refreshments next door. So I hope you have some opportunity to talk a little bit further about the evening. And I hope to see you soon at another event for the department. So thank you.
Thank you again. And everybody just head out next door. That way we can avoid your